quantum mechanical model of atom. So it is the most advanced model of the atom. It's also called the modern structure of the atom. It's based on the quantum mechanical model, quantum mechanics, quantum mechanics. See, we were knowing that the Newton laws of motion are applicable to all macroscopic particles, to all the planets which are orbiting around the sun, and all the particles which are present around us. And we can find out their motions, when they can stop, what is their velocity, or what is their acceleration is, etc., etc. Now, the study of the Newton's law of motion and all of these things is called what? Normal. We say we call it mechanics. Now, that's called classical mechanics. Because when we applied the same principles on microscopic particles or on the subatomic particles, we find that all these laws failed there, which was all proved by the Heisenberg's uncertainty principle. So, our normal classical mechanics concepts, our normal Newton's law of motions are not applicable on microscopic particles or on the particles which are of the subatomic type, which are actually of very small, like protons, electrons, and neutrons. Now, how to describe then their motion? How to describe their velocities and acceleration, etc., etc. Now, because of this, a completely new type of science developed. In fact, you can say new types of physics developed. And the main contributor towards this was the Erwin Schrödinger. The Erwin Schrödinger was actually the physicist who was actually involved mainly in developing independently this modern concept of the physics, which is called quantum mechanics. Though it was working with the Heisenberg also, and both of them gave the same type of results, but we in our syllabus or in our system, we follow more of the Schrödinger's concept. See, remember, the classical mechanics was based on the fact that it was applicable on those particles which were showing only the particle-like motion. And it failed on the particles like subatomic particles, microscopic particles, which shows both wave-like as well as particle-like motion. Therefore, we were requiring to have a new kind of a physics which can describe their motion and other systems which are associated with them. Therefore, Erwin Schrödinger gave us the new concept, new model, new mechanics, which is called quantum mechanics, and that is applicable to all those subatomic particles or to the microscopic particles which are showing wave-like motion. Now, the actual equation, the basic equation from which the Schrödinger started is the equation which is actually written as H psi E psi. Now, this equation, which is written here as such, is basically is a very simple representation of the equation, which was later on, which on solving becomes a very big and complex equation. This here H cap is your Hamiltonian operator. This symbol psi is basically the electron wave, and this is the energy associated with the electron wave, and this is again is the psi. It's basically this whole of this quantum mechanics is a very complex mathematics and as well as physics, which cannot be actually cleared, or it cannot be we can't make you understand at this level, because it is actually is a science, is a type of a science, or it is involving the type of the mathematics which can only be cleared to or which can only be understood at a postgraduate level. So we can only give you I can give you an idea that what exactly this model was. See, the Schrödinger, he being mathematician, basically he has taken what electron, he has assumed the electron to be a particle which is moving in a three-dimensional space, and he was knowing that it is moving not in a particle-like motion, it is showing a wave-like motion. So he was knowing that if he is able to find out the equation which is being followed by this electron in the three-dimensional system, and on solving the equation he can get certain the coordinates, definitely whenever it is required, he can put the values of these electrons in those coordinates, and he can find out what exactly will be the positions of the electron. So what was the major requirement for the Schrodinger was to find out the equation of the electron which this electron will be following in the three-dimensional system. Now for this he needed to have a polar coordinates. So he first took the polar coordinates. The polar coordinates taken were r, theta and phi. R is the distance of this electron from the nucleus, which is also called radial part. And these theta and phi are the angles which describes exactly their position, and these are called angular part. Now all these coordinates, polar coordinates were taken, and then they were determined how they varies and how the electron wave varies. Then he described that since the electron wave is supposed to be like this, let this amplitude to be the psi wave, psi. So what is psi is? Psi is nothing but the amplitude of electron wave, and this amplitude give us what this is basically called the wave function, electron's wave function. And how this wave function varies when the electron moves around the nucleus, we have to determine by the equation which he gave as, I can give you so this is the simplest way, the actual way of writing down the Schrodinger's wave equation. This is the double differential of the psi with respect to the x-axis, y-axis, z-axis, 8 pi square mh square e minus v psi equals to 0. This whole part tells us how these electrons' wave function will vary along x-axis, y-axis, z-axis. This whole term talks about the energy of the electron, and when this equation, how the equation is solved, we get what? 3 answers. Now those 3 answers are called quantum numbers. See, the Schrodinger was knowing that what the previous other scientists have done about the structure of the atom. He was knowing the Bohr's concept, and he was the one actually who was taken over from the de Broglie's and other people. So he was knowing all those facts. He incorporated all those basics which we were knowing, and the only thing which he actually incorporated and he changed from their model is that he basically based his model on the Heisenberg's principles and the de Broglie's dual behavior, and because of this he introduced that the electrons are moving around the nucleus in not in circular, although they are in the circular paths, but their motion is wave-like. It's almost like its path is circular, which we can say it's the same Bohr orbit, but it is not simple particle-like, it's wave-like. Plus that the electron cannot exist at a particular place, it can be present anywhere around the nucleus in the atom, it can be anywhere. And then he gave on solving this quantum numbers, which gave us a concept of orbitals. So basically he divided his structure of atom into 3 stages. The orbits, which are also called shell, which were given by Bohr, he said they are further divided, which was also proved by initially Sommerfeld, into suborbits or subshells, which are further divided into orbitals. So this was his major contribution, that he said the electrons, though are existing in the same orbit, the change what he made is that they are moving in the wave-like motion. They can exist anywhere inside the nucleus, inside the atom, outside the nucleus. And then he introduced the word orbital. He said, though we know the electron can exist anywhere in the atom, but its maximum probability of finding the electron is in particular path, and that path is called orbital. So what is orbital is? It's the three-dimensional space around the nucleus where the probability of finding the electron is maximum. Because we know the electron can exist anywhere. It can exist anywhere in the atom. But yes, for most of the time, it will be present in a particular three-dimensional path, and that path is called orbital. So each orbit or a shell is divided into suborbit or subshells, which are further divided into the predetermined paths where the probability of finding the electron is maximum, and these are called orbitals. We reach to these three stages by the help of those three answers which we have got by solving that quantum wave equation, and those three answers I told you are called quantum numbers. So these are the three basic numbers which we get, which in other form are called quantum numbers. So let us now understand those quantum numbers, and then with the help of those, let's move inside the atom and understand what exactly these orbits or suborbits or orbitals are.